Good morning, dear students. Hope you all are doing good. Today, let us take a look at a question from the book Pathfinder, chapter Fluids. So, let us first analyze the question. To make a candle float stably in water in vertical orientation, an aluminium cylinder of radius equal to that of the candle is glued at the bottom of the candle. So to make this candle float stably, there is a aluminium cylinder you can see here which is glued at the bottom. Length of the cylinder is 1 centimeter. So the length of the aluminium cylinder which is glued to the bottom of the candle is 1 centimeter. Densities of wax, aluminium and water are 0.8 gram per centimeter cube, 2.7 gram per centimeter cube and 1 gram per centimeter cube. So density of this aluminium cylinder is 2.7 gram per centimeter cube. The wax here is 0.8 gram per centimeter cube and water here is 1 gram per centimeter cube. Find the maximum and minimum length of the candle so that it can float in water stably in vertical orientation. So what is the maximum and minimum length of this candle so that it can float stably in water? Radius of the candle is small enough to ignore horizontal shifting of the point of application of buoyant force. So firstly, for the stability of candle, the center of buoyancy must be above the center of mass. So let us take this as a reference level. This is the center of buoyancy and this is the center of mass. The separation between this level and center of buoyancy is LCOB, and the separation between this level and center of mass is LCOM. So for stability condition, LCOB must be greater than LCOM. So before moving forward, let us define a few terms. L is the length of the candle. LCI is the length of the candle immersed. D is the length of the aluminium cylinder. So in equilibrium condition, we can say the weight of the candle plus aluminium cylinder equal to the buoyancy force. So weight equals to buoyancy force. Total weight is mass of candle plus mass of aluminium equal to total volume immersed, volume of candle immersed plus volume of aluminium into density of water. I have cancelled out the G here and here. So in the next step, I have written mass as density into volume and volume as area into length. And we get this expression. We can further simplify this expression to get length of candle immersed in the water. So this length we can get. Now putting in the values in this equation, we get length of the candle immersed in terms of the total length of the candle. Next, let us calculate the center of buoyancy from this level. So from here, where is the center of buoyancy? Okay, so from the base, the center of buoyancy will be at LCI plus D by 2. So this is LCI and this is D. So LCI plus D by 2, exactly at the center will have the center of buoyancy. But we need to calculate the center of buoyancy from here. So LCOB will be this value minus D. So from the base, it is this value. Okay. So from this reference level, it will be LCI plus D by 2 minus D. So putting in the values, we get LCOB is 0.8L plus 0.7 divided by 2. Next, we need to calculate the center of mass of the candle from this level. So what is this length we need to calculate? So we can find the center of mass using the COM formula, M1R1 plus M2R2 divided by M1 plus M2. So if we put in the values we are given here, we get LCOM equals to 0.8 L square minus 2.7 divided by 0.8 L plus 2.7. Let us move on to the first question, that is calculate the minimum length of the candle. So the condition that we can keep here is the candle is such that its surface just touches the surface of water. If it is any more shorter than this, then it will sink. So the length must be such that the surface of the candle touches the surface of water. So the condition we can use here is the length of the candle immersed must be equal to the total length of the candle. If you remember, our very first equation was length of candle immersed equals to 0.8 L plus 1.7. So let us keep LCI equals to L. So LCI equals to L. So putting this value, we get L equals to 8.5 centimeters. So the shortest length of the candle so that it can float stably is 8.5 centimeter, and it will be like this while floating. Next, let us move on to calculating the maximum length of the candle. So this is the free body diagram when the candle is at its minimum length. So this is the mg force which is acting, and this is the buoyant force. We can say that this is stable because the center of buoyancy is above the center of mass. Now let us see what happens as we increase the size of the candle. See, as we are increasing the size of the candle, the center of mass and the center of buoyancy are closing into each other. If we increase the size of the candle any further, the center of mass will go above the center of buoyancy, and the candle will not be able to float stably. Now, how are we saying that as we increase the size of the candle, the center of mass and the center of buoyancy are closing into each other? If you remember, we had calculated LCOB, which was the separation between this level and the center of buoyancy, and L center of mass, the separation between this level and the center of mass. Let us now plot the graph of these two quantities with L, which is the length of the candle. So on the x-axis we have length of the candle. This graph is the LCOM, and this is the LCOB, center of buoyancy. Now always the center of buoyancy should be above this center of mass. Then only this candle can float stably. As we are increasing this value of L, we see that the center of buoyancy is also increasing and center of mass is also increasing. But at one point, the center of mass goes above the center of buoyancy. So for the length of the candle till here, the candle can float stably. So for getting the maximum length of the candle, we can equate LCOM and LCOB. So LCOM equal to LCOB. So if we equate these two equations, we'll get a quadratic in terms of L, and if we solve it, we get L max equal to 18.54 centimeters. So the minimum length of the candle is 8.5 centimeters and its maximum length is 18.54 centimeters.